Welcome everybody, my name is Marcin Hoffmann. I'm with Institute of Radio Communications, Poznań University of Technology. I'd like to say a few words about paper entitled Similarity Measures for Location-Dependent Massive MIMO 5G base stations on-off switching using Radio Environment Map. There are two main ways of improving the spectral efficiency of the 5G and beyond networks. Utilizations of the large antenna arrays, massive MIMO, and dense deployment of small base stations. Both, especially combined together, contribute to the energy consumption. Massive MIMO require more hardware and utilize complex processing techniques, while network densifications makes a lot of base stations being underutilized during nighttime, for example. From this perspective, the energy efficiency of heterogeneous network can be improved by putting underutilized base stations into the sleeping mode. It is switching off some part of base station's hardware. During our previous study, we have proposed a framework based on the radio environment maps and reinforcement learning for this purpose. First, I will describe the overall idea and then indicate issue. We propose to extend the network architecture with the so-called radio environment map. Radio environment map is expected to be deployed on the macro base stations and would contain information about the optimal in terms of energy efficiency set of active pico base stations, related to the given pattern of UE's positions. As we can see, macro base stations report the positions of UEs and observed energy efficiency of the network to the RAM, and RAM responds with the set of active pico base stations. Data in RAM is arranged in entries. Each entry is labeled with the vector of the UE's positions and contains information about the energy efficiency, denoted as Q value, related to all possible configurations of the pico base stations. As massive MIMO is quite complex, including user scheduling, precoding, or dynamic point selection, we propose to utilize the reinforcement learning to learn RAM with proper mapping between patterns of UE's positions and related active pico base stations. And here is the issue addressed in this paper. There would be a lot of similar patterns of UE's positions in RAM, and it is inefficient to go through the procedure of learning them. It's better to map them directly to the most similar RAM entry. In these studies, we have assumed that we have RAM already filled with some data. Now, when new, unknown set of UE's positions is reported, our target is to find most similar entry in RAM, marked as L hat, and use the set of active base stations indicated therein. However, the challenge is to select the proper distance function, similarity measure, for the mapping purpose. There are several state-of-the-art distance functions. The first one is the so-called Hausdorff distance. The idea of the Hausdorff distance is that first, for each UE position, xn is set in set SL, Euclidean distance to the closest UE's position xm in set S tilde L is computed. Then the maximum value of these distances is taken. Next, the procedure is repeated in reversed order, and the max of the two resultant values is taken. In Hausdorff distance, change in the position of a single UE can have a significant impact on the outcome distance value. Next one is the mean distance. Here, the impact of a position of a single UE is reduced. The mean point is computed for both UE's position sets, and Euclidean distance is computed. Also, the distance metric named average distance has reduced impact of the position of a single UE. But here, first, Euclidean distance is computed between every pair of points, and secondly, all these points are averaged. slightly different idea lies under the sum of minimums distance. First, for each UV position xn from set SL, closest point from S tilde L is found, and a related Euclidean distance is computed. These distances are then summed. The same procedure is applied in opposite direction. The sum of minimums results in large distance values in relation to the remaining distance metrics considered in this paper. Thus, we decided to replace the sum with average. This distance metric can be thought of as a balance between the effect of extreme change in a single UV position and the general structure of UV's positions. The performance of the previously mentioned similarity measures is compared with the use of an advanced system-level simulator of the orthogonal frequency domain multiple-access massive MIMO network. The simulator exploits RZF, this is regular zero-forcing precoding, user scheduling, and dynamic point selection. Moreover, a realistic 3D ray tracing model of radio channel is used. Simulation setup assumes that the RAM is already filled with 15 entries, and the target would be to match unknown sets of UV's positions with these in RAM, under two types of localization error. Almost ideal RTK, it is real-time kinematics based, and standard GPS of 6-meter standard deviation. The layout of the considered massive MIMO network is depicted in the figure below. The base stations are marked as larger dots, while users are marked as smaller dots. During simulation, every distance metric was tested under 45 different patterns of UV's positions. Each simulation lasts 15 seconds. There are 40 UVs in total, moving with the speed of 1.5 meter per second. There are 5 pico base stations and macro base station, operating in the same bandwidth of 300 MHz allocated over the central frequency of 3.55 GHz. There is 128 element antenna array installed at the macro base stations, and 32 element array installed at every pico base station. We are considering regularized zero forcing precoder, and base stations transmit powers are of 46 dBm and 30 dBm for macro and pico base stations respectively. The remaining parameters listed in the table are related to the power consumption model. In the figure, there is depicted a cumulative distribution function of energy efficiency achieved by different distance metrics in 45 sets of UV's positions, under almost ideal RTK localization. The major observation is that sum of minimums distance outperforms other distance metrics. Similarly, when RAM utilizes the average distance, it always provides the least energy efficiency gains. Between these two cases, there are the Hausdorff distance and mean distance. They seem to perform similarly. The reason why the sum of minimums is the best is because it balances sensitivity to a single UV movement and the overall structure of UV's positions. On the other hand, average distance utilizes distances between every pair of UV's positions and averages them. In this case, the result can be much affected by largest distances between UVs being, in example, on the opposite sides of the cell, yet close to other users. In this figure, there is depicted a cumulative distribution function of energy efficiency achieved by different distance metrics in 45 sets of UV's positions under less accurate GPS localization. The relations between the performance of RAM under different distance metrics are similar to the case utilizing RTK. Mean distances to suppress. However, now mean distance is better than Hausdorff distance. It may be caused by the ability of mean distance to suppress localization error while computing the mean points of each set. At some points, it's even better than sum of minimums. As it could be expected, the overall performance of RAM is worse as a result of less accurate localization method. Finally, in the bar graph we can see energy efficiency over all 45 sets of UVS positions in relation to the scenario without energy efficiency optimization. Similar hierarchy to the one visible in the previous figures can be observed when considering results average over all tested sets of UVS positions. Under RTK scenario, a RAM-based solution utilizing the sum of minimums distance provides a 56 improvement over a no energy efficiency scenario, while the one utilizing average distance gives only 36%. For the GPS scenario, it can be seen that in the worst case of average distance, average energy gains over no energy efficiency optimization scenario obtained using GPS are equal to 32% instead of 36 obtained using RTK. When considering the utilizations of sum of minimums distance, average energy efficiency gains are reduced from 56% to 48%. Those 56% are related to the RTK scenario and 48% are related to the GPS scenario. Nevertheless, results show that there is still a significant improvement in network energy efficiency while utilizing historical knowledge from RAM together with localization provided by GPS. Finally, the following conclusions can be formulated. The highest energy efficiency gains over a no energy efficiency optimization scenario where all Pico-based stations are active would be observed when the sum of minimums distance was used. The energy efficiency is 56 and 48% higher than the reference scenario while utilizing RTK and GPS as a localization techniques, respectively. Now, thank you for your attention. If you have any questions, feel free to ask.